Chapter 7 of Gardening Without Irrigation, or Without Much Anyway. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Betsy Bush, October 2009. Gardening Without Irrigation, or Without Much Anyway, by Steve Solomon. Chapter 7. The Backyard Water-Wise Gardener. I am an unusually fortunate gardener. After 7 years of struggling on one of the poorest growing sites in this region, we now live on 16 acres of mostly excellent, deep soil on the floor of a beautiful coastal Oregon valley. My house and gardens are perched safely above the 100-year flood line. There's a big, reliable well, and if I ever want more than 20 gallons per minute in midsummer, there's the virtually unlimited Umpqua River to draw from. Much like a master skeet shooter who uses a .410 to make the sport more interesting, I have chosen to dry garden. Few are this lucky. These days the majority of North Americans live in urban struggle. Their houses are as often perched on steep, thinly soiled hills or gooey, difficult clay as on a tiny fragment of what was once prime farmland. And never does the municipal garden have one vital liberty I do, to choose which 1/6 of an acre in his 14-acre backyard he'll garden on this year. I was a suburban backyard gardener for 5 years before deciding to homestead. I frequently recalled this experience while learning to dry garden. What follows in this chapter are some strategies to guide the urban in becoming more water-wise. Water conservation is the most important first step. After it rains or after sprinkler irrigation, water evaporates from the surface until a desiccated earth mulch develops. Frequent light watering increases this type of loss. Where lettuce, radishes, and other shallow-rooting vegetables are growing, perhaps it is best to accept this loss or spread a thin mulch to reduce it. But most vegetables can feed deeper, so if wetting the surface can be avoided, a lot of water can be saved. Even sprinkling longer and less frequently helps accomplish that. Half the reason that drip systems are more efficient is that the surface isn't dampened and virtually all water goes deep into the earth. The other half is that they avoid evaporation that occurs while the water sprays through the air between the nozzle and the soil. Sprinkling at night or early in the morning when there is little or no wind prevents almost all of this type of loss. To use drip irrigation, it is not necessary to invest in pipes, emitters, filters, pressure regulators, and so forth. I've already explained how recycled plastic buckets or other large containers can be improvised into very effective drip emitters. Besides, drip tube systems are not trouble-free. Having the beds covered with fragile pipes makes hoeing dicey, while every emitter must be periodically checked against blockage. When using any type of drip system, it is especially important to relate the amount of water applied to the depth of the soil to the crop's root development. There's no sense adding more water than the earth can hold. Calculating the optimum amount of water to apply from a drip system requires applying substantial practical intelligence to evaluating the following factors: soil water-holding capacity and accessible depth, how deep the root systems have developed, how broadly the water spreads out below each emitter, dispersion, rates of loss due to transpiration. All but one of these factors, dispersion, are adequately discussed elsewhere in Gardening Without Irrigation. A drip emitter on sandy soil moistens the earth nearly straight down with little lateral dispersion. 1 foot below the surface, the wet area might only be 1 foot in diameter. Conversely, when you drip moisture into a clay soil, though the surface may seem dry, 18 inches away from the emitter and just 3 inches down, the earth may become saturated with water, while a few inches deeper, significant dispersion may reach out nearly 24 inches. On sandy soil, emitters on 12-inch centers are hardly close enough together, while on clay, 30 or even 36-inch centers are sufficient. Another important bit of data to enter into your arithmetic: 1 cubic foot of water equals about 5 gallons. A 12-inch diameter circle equals .75 square feet. A equals pi times radius squared. So 1 cubic foot of water, 5 gallons, dispersed from a single emitter will add roughly 16 inches of moisture to sandy soil, greatly overwatering a medium that can hold only an inch or so of available water per foot. On heavy clay, a single emitter may wet a 4-foot diameter circle. On loams anywhere in between, 5 gallons will cover a 4-foot diameter circle about 1 inch deep. So on deep clay soil, 10 or even 15 gallons per application may be in order. What is the texture of your soil, its water holding capacity, and the dispersion of a drip into it? Probably it is somewhere in between sand and clay. I can't specify what is optimum in any particular situation. Each gardener must consider his own unique factors and make his own estimation. All I can do is stress again that the essence of water-wise gardening is water conservation. Optimizing space. Planning the water-wise backyard garden. Intensive gardening is a strategy holding that yield per square foot is a supreme goal. It succeeds by optimizing as many growth factors as possible. So a raised bed is loosened very deeply without concern for the amount of labor, while fertility and moisture are supplied virtually without limit. Intensive gardening makes sense when land is very costly and the worth of the food grown is judged against organic produce at retail, and when water and nutrients are inexpensive and are available in unlimited amounts. When water use is reduced, yield inevitably drops proportionately. The backyard water-wise gardener, then, must logically ask which vegetable species will give him enough food or more economic value with limited space and water. Taking maritime northwest rainfall patterns into consideration, here's my best estimation. Water-wise efficiency of vegetable crops in terms of backyard usage of space and moisture. Efficient enough. Early spring-sown crops: peas, broccoli, lettuce, radishes, Savoy cabbage, kohlrabi. Overwintered crops: onions, broccoli, cauliflower, cabbage, fava beans. Endive, kale, garden sorrel. Indeterminate tomatoes: giant kohlrabi, parsley, leaf and root. Heirloom summer squash, sprawly. Pole beans. Herbs: marjoram, thyme, dill, cilantro, fennel, oregano. Root crops: carrots, beets, parsnips. Marginal: Brussels sprouts, late, potatoes, determinate tomatoes, rutabagas, eggplant, leeks, Savoy cabbage, late, peppers, small fruited. Inefficient: beans, bush, snap, peppers, bell, broccoli, summer, radishes, cauliflower, scallions, bulb onions, celery, sweet corn, lettuce, turnips. Have fun planting your own water-wise garden. More reading. About the Interlibrary Loan Service. Agricultural books, especially older ones, are not usually available at local libraries, but most municipal libraries and all universities offer access to an online database listing the holdings of other cooperating libraries throughout the United States. Almost any book published in this century will be promptly mailed to the requesting library. Anyone who is serious about learning by reading should discover how easy and inexpensive, or free, it is to use the Interlibrary Loan Service. Carter, Vernon Gill, and Tom Dale, Topsoil and Conservation, Norman, Oklahoma, University of Oklahoma Press, 1974. The history of civilization's destruction of one ecosystem after another by plowing and deforestation, and its grave implications for our country's long-term survival. Cleveland, David A. and Daniela Solari. Food from Dryland Gardens: An Ecological, Nutritional, and Social Approach to Small-Scale Household Food Production. Tucson, Center for People, Food, and Environment, 1991. World-Conscious Survey of Low-Tech Food Production in Semi-Arid Regions. Faulkner, Edward H. Plowman's Folly, Norman, Oklahoma, University of Oklahoma Press, 1943. This book created quite a controversy in the 1940s. Faulkner stresses the vital importance of capillarity. He explains how conventional plowing stops this moisture flow. Thoth, Henry D. Fundamentals of Soil Science, 8th edition, New York. John Wiley & Sons, 1990. A thorough yet readable basic soil science text at a level comfortable for university non-science majors. Hamaker, John D. The Survival of Civilization, annotated by Donald A. Weaver, Michigan and California, Hamaker Weaver Publishers, 1982. Hamaker contradicts our current preoccupation with global warming and makes a believable case that a new epoch of planetary glaciation is coming, caused by an increase in greenhouse gas. This book is also a guide to soil enrichment with rock powders. Nabhan, Gary. The Desert Smells Like Rain, a Naturalist in Papago Indian Country. San Francisco, North Point Press, 1962. Describes regionally useful Native American dry gardening techniques. Russell, Sir E. John, Soil Conditions and Plant Growth, 8th edition, New York, Longmans, Green & Company, 1950. Probably the finest, most human soil science text ever written. Russell avoids unnecessary mathematics and obscure terminology. I do not recommend the recent in-print edition, revised and enlarged by a committee. Smith, J. Russell. Tree Crops, A Permanent Agriculture. New York, Harcourt, Brace & Company, 1929. Smith's visionary solution to upland erosion is growing unirrigated tree crops that produce cereal-like foods and nuts. Should sit on the family Bible shelf of every permaculturist. Solomon, Stephen J. Growing Vegetables West of the Cascades. Seattle, Sasquatch Books, 1989. The Complete Regional Gardening Textbook. Solomon, Stephen J. Backyard Composting. Portland, Oregon. George Van Patten Publishing, 1992. Especially useful for its unique discussion of the overuse of compost and a non-ideological approach to raising the most nutritious food possible. Stout, Ruth. Gardening Without Work for the Aging, the Busy, and the Indolent. Old Greenwich, Connecticut, Devin Adair, 1961. Stout presents the original theses of permanent mulching. Turner, Frank Newman. Fertility, Pastures, and Cover Crops Based on Nature's Own Balanced Organic Pasture Feeds. San Diego, Radehaver, 1975. Reprinted from the 1955 Faber and Faber edition. Organic farming using long rotations, including deeply rooted green manures, developed to a high art. Turner maintained a productive organic dairy farm using subsoiling and long rotations involving tilled crops and semi-permanent grass-herb mixtures. Vanderleiden, Fritz. Fred L. Troyes and David K. Todd. The Water Encyclopedia, 2nd edition, Chelsea, Michigan, Lewis Publishers, 1990. Reference data concerning every possible aspect of water. Weaver, John E., and William E. Bruner. Root Development of Vegetable Crops. New York, McGraw-Hill, 1927. Contains very interesting drawings showing the amazing depth and extent that vegetable roots are capable of in favorable soil. Widtsoe, John A. Dry Farming, A System of Agriculture for Countries Under Low Rainfall. New York, The Macmillan Company, 1920. The best single review ever made of the possibilities of dry farming and dry gardening, sagely discussing the scientific basis between the techniques. The quality of Widtsoe's understanding proves that newer is not necessarily better. End of Chapter 7. End of Gardening Without Irrigation, or Without Much Anyway, by Steve Solomon.